Welcome to the next part in our automation video series. I'm Mitch from the Betfair automation team. I'm here with Darryl Woodford from the Cipher Sports Technology Group. In the previous video, we covered a lot of things, especially around US sports and the exchange and how you get your hands on some good data. So in this video, we'll cover more in depth around how you create a machine learning model and the data science concepts behind it. So Darryl, welcome.
Thank you.
So we spoke about different data sources. They seem like a real headache. How do you manage to match up all these sources, especially in individual sports or player props?
Yeah, I mean, it's definitely a challenge, right? So particularly where you're dealing with multiple different data sources, it's very hard to find any kind of coherent ID. If you're in the ecosystem of one of the bigger providers, a Sportradar or a Stats Perform, they'll often have an ID that ties together their player stats that links into a team ID that covers their team stats that links into an ID that you can find in odds feeds. But for the majority of times, that's not what you're going to get. The majority of the times, you're going to get some data that's got Serena Williams, some data that's got S Williams, some data that's got S. Williams, some data that's got Williams, S. And you're basically trying to merge all of those together. In the NBA landscape, you've obviously got all the players who've got like senior or junior, sometimes with a full stop, sometimes without a full stop, sometimes spelled out in full. So at the initial stages of building any kind of model, whether you're talking machine learning or you're talking simulation, you're going to have to do a lot of data cleaning. You're going to have to figure out, okay, how do I pull all these data sources together? And also when you actually deploy that model into any kind of production, whether that's just for your own betting or whatever it is, you're going to have to deal with the new players who come out, who make their NBA debuts, who get called up from G League. You need to be able to have enough manual overrides in the system that you can account for those as they go into the different data sources. Inevitably, you're going to be spending a lot of time doing that. If you're betting into Betfair, it saves you one step, right? Because you're not focused on pulling in odds from 10 different bookmakers and finding out where you can get the best price. You're basically building a system that's solely designed to trade on the exchange. And you would be able to pull from Betfair how players are named, how teams are named, how they go into markets.
And just with the some of the things on Betfair, like selection names in Betfair don't have apostrophes, so if you're trying to match up a name between sources, you might have to remove apostrophes. Or what I found in scraping data from web sources, especially where you've got non-standard characters in names, some of the Python libraries can actually fall over if they're not encoded in the correct way.
Unicode and ASCII conversions were the bane of my existence for many years.
Yeah, and sort of how will you handle for neutral games?
Yes, I mean often we're trying to cope for home field advantage. Home field advantage is an interesting topic in the last few years because any data set that you're looking at now also probably includes a COVID period where home field advantage is very different because you're playing in empty stadiums, sometimes entire tournaments at neutral venues. But in the context of regular sports, so NRL Magic Round or the NRL games in Vegas, you've got to deal with the challenge of, okay, my model has normally got a data where one team is home, one team is away. We've calculated a home field advantage based on that, or the model has inferred a home field advantage because you're predicting a home team score and an away team score. But you've probably only got 10 games in the last, 20 games in the last 3-4 years that have got a neutral field. So how do you account for them? Often the answer is just don't bet them. If you're relying on an ML approach and you've got some kind of unique factor that you're not going to have enough data on, the answer is probably just skip that game, pretend it didn't happen for all intents and purposes, other than storing the historic data. The other challenge you've got is Australian sports in particular, the seasons are pretty short by comparison to MLB or NBA. So you've only got a small sample of data. If let's say one of your features is a 3-game weighted average, one of your features is a 10-game weighted average, you don't want to have to throw out every game that was within 10 games of a neutral game because you're going to massively decrease the size of your data set. You've already probably only got, I don't know, how many games are there in an AFL season?
25 max, yeah.
So you throw out, if you have to throw out 8 of those, 9 of those, you're massively minimizing your data set. So ultimately, what I would do in the first instance is simply add a field in that is a binary 1-0 that tells the model this was a neutral game, this was not a neutral game. See if it's able to pick up enough from that. That would be my starting point. But you may also look at, okay, I want to manually calculate what the home field advantage is and adjust the different stats to account for that. So, if you look at historically, a team is 3 points better when they're at home. Maybe you have to account for that manually in your data preparation, your feature engineering process.
And it would be quite interesting in the AFL context where multiple teams have the same home ground. So if, say, Collingwood play Melbourne at the MCG, both of them, it's their home ground, but one's away and one's home. So
I think Greg did a video for Betfair before where he talked about AFL in more detail. I'm definitely not an AFL natural, but I do know from listening to Greg that that's a common point of problems. Also, how do you account for the difference between something like a Geelong home game versus a game that's played in Adelaide, for example? Is that the same? Is that different? Does the travel time involved make a difference? That's often a feature that we've put into models in the past. If you have to travel across the US, is that different than going from New York to New Jersey in terms of the impact on team performance?
Yeah, and so I've talked about being the longest journey in football being the Perth-Brisbane flight, and historically both Brisbane teams and Perth teams have performed well in their respective away zones.
Yep.
So that's quite interesting. How would you handle sort of missing data or sort of weird outliers?
Yeah, so we briefly touched on this last time. One of the challenges with some of those AutoML libraries is that they will try and impute values, right? So often with Azure's, Microsoft's ML Studio, for example, if you upload a bunch of data and there are a bunch of missing values, by default, it will try and either replace them with zeros or replace them with the mean, so kind of the average of the other data in that column. I don't like that approach. I think what you need to understand, okay, is that missing because it's actually a zero, which is sometimes the case with data providers. Because of the way that different databases store data, sometimes nulls and zeros just get confused in the data storage process. So the first thing you need to understand, is that actually a zero? The second thing you need to understand is that missing for some reason? For example, is it a first half statistic for a player who only came on after half time in a soccer game? In both of those cases, you don't want to do either of the automated approaches. I think it's a case of, so it's a bit of a case of you need the domain knowledge. You need to understand what's happened to the data in the first place, and then you need to make a deliberate decision on how you want to handle that data. If you're missing, if 60% of a particular column is missing, are you better off just removing it? Or are you better off making a decision to include it, but adding some signifier yourself that the model can understand that this was a player who only came on at halftime? So there's a bunch of different ways to do it. But yeah, in general, I think my advice would be make a deliberate decision on what you're doing. Don't just allow a library or an automated tool to make that decision for you, because you ultimately garbage in, garbage out with ML.
Yeah, absolutely. And then what about outliers?
Yeah, so outliers, I think, again, it's about being deliberate. So what I would usually do is I take the data that we're about to feed in, I put it into something like a Jupyter notebook, or even a visualization tool like a Tableau or a Power BI, and I try and, visually see, are these outliers or are they just the top of the curve? If they are outliers, I would try and look at the entire row of data that outlier sits in to understand, to spot check it. So go back to other data sources, go back to independent places, see if that is actually a fact, or is there a typo? Is it a calculation that somebody at some point has done in Excel and it's messed up the decimal places? Try and understand what's happened. And if it is a valid piece of data, I'd want to understand, what was the situation that led to it, so that when training the model and also when putting in any kind of guardrails for the inference process, you can understand, this is a situation that has occurred, how would I deal with it in production? Yeah,
absolutely. You do see sometimes those extreme data values. For example, in soccer, where Australia has played, one of the small Pacific nations, and Australia's won 18-0, and one player scored 12 goals. Yeah. Something like that has happened in the past. Yeah, handling that in machine learning model, is interesting. And
you need to deal with it, right? You can't, because let's say one of your features in a predictive model was goals, and you've got a 10-game weighted average. For the next 10 games, that 18 goals is going to throw that number out. So you need to make a decision on how you deal with it. Do we just ignore that game and say, for the games that we're going to simulate, we're going to exclude those in the future? or do you include it but add some other kind of signifier that it was I'd use the phrase minor league game, but you get the principle of that it's somehow different from the standard game that they were playing.
Yeah. Well, it sounds like you're part detective and part statistician. How do you decide which features are actually going to help you predict the outcome?
Yes, I guess features in this context, as I said, our NFL models probably have like 150 different features going in. Some of those are raw statistics, so either a team or player. Some of those are things that we've calculated ourselves. And you've got a couple of approaches, right? You can analyze, three. You can look at the data yourself and say, okay, I'm a domain expert. I understand the rules of NFL, so I have a feeling, I have intuition that these 12 statistics are going to be important. I want to make sure that those are evident in the model that we're generating. You can go down the route of automated feature engineering, which is essentially an approach of saying, okay, we know what we're trying to predict, we know what our input features are, and effectively the library will give you an importance factor for those different features, which you can either then accept as is, or you can sanity check yourself. Often that's a good exercise regardless, because if you've got some kind of data leakage, you've got one of your statistics that somehow you've forgotten to shift, so it's actually data from that game rather than from before that game. The fact that that just shows up as 98% of feature importance probably tells you, okay, I need to understand what's happened there. And then the third approach, as I say, you can basically run those same kind of experiments yourself. You can say, okay, how predictive of team total points is a combination of run meters, tackles, and try assists, for example. And thus you can kind of narrow down what features you want to use yourself. Essentially, it's important to find novel features. If you're using the same data as everybody else, you're probably not going to find too many edges, because as we talked about before, there's a lot of computational power thrown at it. If everyone's putting the same kind of things into very similar models, you're going to get very similar outcomes. So having some kind of degree of creativity in that feature creation process, feature engineering process is important. The other consideration is the more features you have, the more difficult it will be, the more computationally expensive it will be to train the model, and the more computationally expensive it will be to run the model. So there's a whole science there's a whole science in data science. It sounds weird, but you get what I mean. It's called dimensionality reduction, which is basically you want to reduce your features to the minimum possible set that still gives you the outcome that you're looking for, because that brings with it a whole bunch of benefits further down the pipeline. In that, your whole process of collecting the data, processing the data, feeding that data into the model, and dealing with the outcome, all of that becomes a lot more efficient the less features you have to deal with.
Yeah, absolutely. There is definitely a balance between adding those new features and the complexity that they bring. It's a delicate balance, right? You can make it too unwieldy or difficult to interpret, or might not capture the nuance of the data, right? Yeah,
exactly. I mean, if you simplify too far, then you're not going to capture where there might be market inefficiencies, right? It's a well-trod example, but Moneyball obviously was around certain statistics in baseball being undervalued, and thus teams were able to get an advantage by signing the players who did well in that area more cheaply. The same kind of thing applies in betting, right? If a particular statistic or two aren't being generally considered by the market when evaluating a match bet or a player prop or whatever it is, that's where you might be able to find an inefficiency in the betting market. And so by incorporating those additional statistics, you're able to find an advantage.
Definitely, and that's when that domain knowledge comes into play.
Yeah, exactly. And just keeping on top of what's happening, right? Like new statistics get kept some seasons that never existed before. You obviously can't train those historically, but how quickly can you incorporate those into your modeling process? A new statistic in baseball, for example, you could adopt more quickly because each team plays 162 games, whereas it's a lot harder to do that for something like NRL, AFL, before you just don't get the build-up of data quickly enough.
Yeah, definitely. And are there like automated feature selection techniques?
Yeah, so I mean, the same way we talked about in terms of like feature engineering and in terms of being able to automated feature selection, there's also automated feature reduction. So there's approaches that you can say, okay, and I talked about before about like AutoML tools, right, that will show you the importance that they've assigned to each variable. Often what you can do is then, if you know that the top 30 variables accounted for the vast majority of the model's predictiveness, you can say, okay, let's drop anything below that, retrain the model, see if you get a similar level of accuracy. And if you do, then obviously you've significantly simplified your whole process.
Definitely. It sounds like selecting your features is an ongoing process, not just setting it up once. How do you decide when it's time to revisit your feature selection and make adjustments?
Yeah, so I mean, it's an interesting one, right? So there's a challenge there. You don't necessarily, well, you don't want to be retraining your model after each new set of data comes through. There are certain times when you will need to retrain it. So, rule changes, general changes in the scoring environment. COVID was another good example of this, right? We saw fairly significant changes in a lot of sports. But I mean, profit testing is one way of doing it. If you know that the model historically has, gone at this level over 1,000 games, and then for 1,000 games it drops below kind of a margin of error. That's obviously a good signifier of that. You've got the other metrics that you can use to keep track of a model. So if you're predicting something like margin or total, you can look at mean squared error or correlation metrics to see is my current data significantly different than the data that I originally trained on. If so, it's probably time to retrain it and incorporate that new data. So I mean, like you were saying before, it's a balance, right? It's a balance between not overdoing it, but making sure that you're able to adapt to any changes in the underlying sport. So that's where domain knowledge again comes in.
Yeah, exactly. And then if you're aware there's some sort of fundamental change in the market, then it's good to perhaps for that period throw out the data. Or as an example, like when the UK racing shut down during COVID, pretty much everyone that I'm aware of, their horse racing models fell over because all the British money was coming into Australian racing.
Yeah.
It was only racing globally that was still going. So there was a huge change, fundamental change in the market for that period while the UK racing wasn't running. And
did it pretty much revert to the mean, the norm afterwards?
Yeah.
Okay.
Yeah. Once the UK racing resumed, yeah.
Yeah.
Yeah. What can you tell me about cross-validation?
So, I mean, it's basically a case of how you want to test your model, right? So you've got the idea of, train and test splits. So you never want to evaluate your model on the same data that you were training your model on. Doing that's a recipe for disaster and overfitting and so on.
Yeah.
But equally, if you're using the same test set continuously, you run the risk of effectively and particularly as you get into some kind of custom loss or profit testing, you run the risk that you're basically now you found a model that works, that's built from your training set and is optimized on your test set. So effectively what you want to be trying to do is take different strands of your data and make sure that within each of those different subsets, your model still works. Trying to think of a good example, but yeah, and in the US, in Major League Baseball, for example, does your model work both on American League and National League? Does it work with both day games and night games? How do you make sure that you've got a stratified sample that you want to test on?
Yeah. How would you go about setting up a simple regression model, especially if you don't have sort of programming experience?
Yes, I mean, you can do this. Excel can build you essentially a basic regression model. It's one of the good ways of getting started. A lot of the more mathematically minded packages, so things like R, will allow you to do that. I mean, I'm biased towards Python, and I would probably recommend go to one of those starting sources for Python, Code Academy. The one I really like is Learn Python the Hard Way.
Oh, okay, yeah.
But some of those, and most of those will give you the basics. If you look at a data science package like Pandas, you look at its documentation, again, it will have an example on how you build a regression model. Pandas essentially is just a spreadsheet in many ways, right? You've got a data frame of your data, you can run commands on it. that would probably be my starting point. And then, that knowledge then isn't wasted. It's also transferable to how you build up into the higher levels of the data science.
Yeah. And sort of what's the difference between linear and logistic regression?
That's a test question. So effectively linear regression, you're trying to predict often a variable, right? So you're basically saying, given these 5 different input variables, I want to predict margin. Yeah. And you'll effectively get a graph, a line that will say, okay, you want this ratio of this, you want this ratio of that, you want this ratio of this, and you'll get to your outcome. Logistic regression often used more for classification tasks. So you want to say, do I want to bet, yes or no? One, and it will return often a probability that you do bet. So it will return 0.66. And then you have to make an inference from that of, whether you take that action or not. So they're not as similar as they perhaps sound.
Yeah, definitely. Sort of, what's the process involving training these sort of regression models?
So we covered it before about so your train and test split, right? Yeah. So effectively, you want to the way I'd approach it in Python would be I'd pull that data into a pandas data frame. I'd basically identify what the columns I want to use as my features are, and I'd identify the column that I want to use as my target are. And then I'd use a combination of pandas and something like probably scikit-learn to actually go in and say, okay, given these feature columns, this is what I want to predict. Allow it to basically build what that is. And then you take that same, before that you do your train test split. Yep. So you build that on your train sample, you then apply it to your test sample, you look at what your difference between your inferred value and your actual value is in the test sample, and see if that's within the kind of bounds of what is acceptable for your current use case.
So we've got our data set into data frame. Sort of what are our pre-processing steps? Yeah,
so different kinds of machine learning frameworks like their data presented to them in different ways. What you'd often want to do, and we talked a bit about like handling missing values, handling kind of null values. So effectively the first stage is a lot of data cleaning, making sure that what your data is matches kind of what you're expecting it to be. Your next step is your pre-processing. So for a lot of cases, machine learning models prefer things to be normalized, and they prefer, in some cases, it to be like a value between 0 and 1. And that's why, that's kind of why outliers are significant, because if you've got a massively outlying value, then everything else kind of gets squashed together during a normalization process. So you kind of go through those kind of pre-processing steps, and then you'd basically you've got 2 options. You can either then pass that into one of those frameworks that I talked about before. So whether you're training models manually with XGBoost and basically passing in a NumPy or a pandas data frame into it, or you can often pass that data and then into one of those AutoML frameworks. Those AutoML frameworks will do a lot of that pre-processing for you, but what you lose with them doing it is the understanding of exactly what they have done. They're getting a little bit more transparent because of some of the regulations around transparency and models generally. But in general, they're still quite black box in what they do, both during that pre-processing and during that training stage. So that's your toss-up between, you'll need a lot more programming and a lot more coding to be able to do it manually. But you understand what's happened. Whereas if you feed it through an AutoML, it's a lot quicker, you'll get started a lot quicker, you'll get a result a lot quicker, but you lose some of that visibility on what's happened in the pipeline.
Yeah, it can be a little bit of a black box, And that scaling is important, especially in sports and racing as well, where you've got some values that are just really, really high. Like, for example, prize money in horse racing, you can get some races that are worth, tens of millions of dollars or whatever that is, and that's a huge number in terms of context of a country race, which can be, $10,000. Yeah. So that scaling is quite important. How do you make sure you're on the right track with the machine learning model?
Yes, I guess so. We talked about this. We talked about different ways of evaluating a model, right? And I think it comes back to a similar kind of thing. You've got multiple stages at which you can evaluate it. So is your are your predictions close enough to the actual data? So that's where you've got things like correlation analysis, mean squared error, root mean squared error, those kind of metrics that will tell you, okay, how close am I to what I was trying to predict? From a pure data science perspective, that's probably the answer. From a Betfair, from a building a sports betting model perspective, I still recommend profit tests. Getting access to odds data can be tricky. As you talked about, Betfair do have it, and there's some good tutorials on how to kind of extract it from the source data. But you need to understand, okay, if I did place this bet at this time, would it have been profitable? If I ran this entire betting strategy over the course of a season, would it be profitable? Because you can be very close to accurate and not profitable. And I think that's maybe something that slightly gets overlooked is, the odds themselves tell you the story of a market, right? Effectively, if the odds are $2 each side, the market expects that to be 50-50. If your answer is 51-49, then you're probably not, even if you bet the 51 side continuously, you might not be profitable.
Yeah, exactly. And obviously, Betfair takes commission off winning positions. So for a sports market, it's 5%. So if you've only got sort of a 1% edge, then 5% commission, you're going to be, you won't be profitable.
Yeah, so I mean, and that comes into your profit testing approach, right? So you have to consider what actual odds were and then what the net odds were, essentially, when you're profit testing, which again might be different data than you'd use in the training process, because if you are feeding odds into the training process, it's often useful at that point to convert them into probabilities. So, 0.57, 0.43, math off the top of my head, because they are more useful often in the process of trading a model than the actual raw odds.
Yeah. Especially with logistic regression type models where it spits out a probability of a result, right?
Yeah.
How would you avoid sort of overfitting in a machine learning model?
So a few aspects. So you want to obviously make sure that you're splitting your data. If you train on the full set of data and then test on the full set of data, you're pretty much guaranteed to overfit because the model is basically just trying to make everything look as close to the outcome as possible. Being very aware of what you're feeding the model is important. Often when you're creating rolling averages and you're creating new data points, it's easy to inadvertently give the model some access to something it shouldn't have access to. We're dealing with time data here a lot, right? So if a team change got made at 12 o'clock, but your odds were taken from 12:05, then the market at that point probably has knowledge of that team change. So if you're feeding those in as an input, then you're giving it information that it wouldn't have if you were placing the bet the day before. So you have to be very careful, and that also gets challenging across time zones, right? So some data sources are UTC, some data sources are Eastern Time, US, some data sources are Australian time. You have to be careful with that. Again, the cross validation or the testing through different stratifications of the data is important. Overfitting can easily get hidden. So it might be that it's fit to a very specific case, and it will only recommend betting in that particular type of situation, but that situation actually won't arise very often, and so you'll effectively just it will turn into noise essentially. Essentially you have to be, and it comes back again to what I was saying before about being very conscious and aware of what you're feeding into the model at different times and how you make those decisions on handling different types of data. All of those things can lead to everything.
Yeah, data leakage is definitely a sneaky problem that could mess up your predictions, definitely.
Yeah.
And referring back to the session we had with Paul, if you put a model into production and start betting it and it has a horror run, you can be tempted to turn it off, and then sort of going back and retrain it. It's important to avoid that temptation. So we talked about markets overreacting to things. You could be overreacting to essentially what is just a dip in your model's profitability. So It's important to let it run for a more extended period of time just to reassess or to get a really good picture of how it actually will perform in production. So let's move on to simulation models.
Yep.
Can you tell me a little bit more about them in the context of Markov chains or Monte Carlo type simulations?
Yes, I mean, so essentially what we're trying to do with simulation models is very similar to what, for example, game developers do. Part of my background is kind of game design. And you're trying to build an engine that allows you to run that game or that sporting event, right? So in baseball, you're effectively, I like baseball because it's a nice example, but you're effectively building a state system, right? There's a series of different states that a game can be in. You can have a runner on first, you can have a runner on first and second, you have a runner on third, second, third. And the outcome is more or less, if a player hits a double, you know what's going to happen from there onwards. So it allows you to basically build that simulation model of how a game is going to unfold, and then to take your, for example, player predictions as input into that simulation. So if we know that a chance of a player getting a single is 15%, the chance of them getting a double is 4%, the chance of them getting a home run is 1.5%, for example, in that particular matchup, we can play those different scenarios out from that point onwards and explore what could happen and what could happen in different iterations of that game. So effectively what we're trying to do is say, okay, we'll play this game out 10,000 times. Across those 10,000 simulations, we're going to explore a whole heap of different scenarios. You can subset those simulations, so you can say, okay, given, and this is useful when you get into things like same game parlays, you can say, for example, in games that the Angels win, what is the chance of this player getting a home run? What is the chance of this player getting a hit? And that allows you to explore some of those correlations that exist within the context of an individual game. The other scenario in terms of like simulations is what we talked about in terms of futures, right? So we're trying to run a season 10,000 times. In one way or another, we'll get to a probability of an individual game result. So Lions, Collingwood, for example, let's say the Lions win on average 42% of the time. Basically, in one of our simulations, they've got a 42% chance of winning. So over 10,000 simulations, they'd win, bad math, 4,200 of them. But each, from that time where they win that game, then the second game that they play will have its own probabilities. And that's kind of how we get to, some of those probabilities around top four or make playoffs, make finals, etc. That is a powerful approach for exploring futures, and generally I think futures is one of the less efficient markets that's out there. You've got to account for the likelihood of players getting injured. The Angels without Ohtani and Trout are very different than the Angels with Ohtani and Trout. So not anymore, Ohtani's gone, but how would you account for the probabilities there? And so it's an approach that allows us to potentially also trade those markets, right? So futures is a great market for trading because you don't necessarily have to wait for the season to finish to realize the value that you've created by taking a position on a particular team.
And there's one thing on the exchange where Australian customers can't bet in play on sport without sort of calling up. But futures markets you can trade while games are being played. So it's quite a good thing to do, and especially in sort of really important games where it can decide whether a team makes the 8 or not, or top 4. Then you can trade during that game and make a profit from there. Cool. Well, that wraps up our session with Darryl today. Thank you for watching.
Imagine what you could be buying instead. For free and confidential support, call the number on the screen or visit the website.